any questions for the exam quiz?
Maybe we can turn this tutorial into something like, if it's allowed.
Like something related to the, like to study?
Only 4 days.
Okay, if you like.
Yes?
If you have any questions, anything. So the thing is, the problem with that is that we're going to miss like the tutorial of this week.
Yes.
Okay. What we can do is that we can go very fast over the tutorial, and after that we can do something.
Okay.
Yes.
Yes.
Okay.
Absolutely yes.
Okay. Let's do that. Okay. Today we are going to talk about density of states. Okay. Do you remember what does it mean, density of states?
Oh, it was just this morning.
Yeah, it was like the function inside the integral of the Helmholtz energy.
Okay, but like what does it mean? What does it tell you?
We can't remember because it didn't.
It was like the
Yeah,
last minute.
Last
Okay,
minute
okay.
of the lecture.
Great. So it's a good way to continue. Okay. So density of states, it's the number of states of a system at it's how many states are available for a certain energy, for a center, for a specific energy of the system. Do you remember that we saw the pendulum, like the phase space? Okay, we have position, momentum, and we saw that each of the shells of the ellipse are energies, right? Mm-hmm. So in the continuum, when you have a continuous system that like for example the system moves around this ellipse, then there are infinitely many states, right? And then you can just plug it as a derivative of the volume of the total energy that is below that level. But in quantum, you don't have continuous systems. So you have like, you can actually don't have like good points of momentum or position, right? Because you have the uncertainty principle. Mm-hmm. So instead of this, we do something different. Okay. So this is the geometrical intuition for classical statistical mechanics. And for quantum, let's start with an example. First, you know this relation in most systems in quantum mechanics, you relate the frequency, right, with the wave vector, right? Because this is energy and this is momentum. So usually it's something, for example, a free particle would be something like this. And this would be h bar omega. You can relate it by this. And this would be k square, h bar square, or 2m. So you have like omega as a function of k. And this is this is what is called the dispersion relation, right? Okay, so this is just a small reminder. Let me put the lines here. Okay, so do you have any idea how you compute the density of states for a free particle on a box? Do you remember how did we do it the first time? So, first,
You just did an analogy between dispersion relation and density of states.
no.
What exactly? Why did you go to?
Okay, so this is a reminder of quantum. Okay.
Okay.
And now we're going to see how actually the class is going to be to build that relation. Okay?
Okay.
That's what we're doing now. Okay? So, do you remember how we computed the density of states? First, we computed the total number of states, right? Okay? So, this is important. Today I'm going to use, this is energy as a variable, okay? And epsilon is the energy of the system.
Okay.
Okay? So, so we have a free particle. Do you remember what's the formula for intake? Oh, so I just read it there. Right? Over 2m. So do you remember what's the formula for the momentum in a particle on a particle in a box? It is n pi over L, right? This is the quantization of momentum. Okay, so this should be h squared p squared. But here is, we have a three-dimensional system, okay? Because we are on a box. So actually this is volume. Okay. So the sizes of the books are the same. Okay, so until now, this is quantum mechanics 1. Okay, so now the way we counted the states, it was how many, for a given energy of the system, epsilon, how many states are, how many different combinations of this energy do we have? So we have all, sorry. So this is a function of the of the general problem, right? And we have, you can think of the epsilon as a cutoff. You can have energies up to that level, okay? So this would be the energy of the system. So we will have something like this, okay? This is energy. Okay, and this would be just okay. So geometrically, what equation is this? How can you interpret, as we did with the classical case, that we saw that this was an ellipse?
This is an ellipse.
No,
Sphere. Sphere.
yeah. Great. Okay, so this is the equation for a sphere. So let me write it this way, so it will be very easy to see. Okay. Right? So this is the total number of states. This is how many states do we have until we get to epsilon, right? These are the quantum numbers, and we can increase them consequentially. So then, how do we take the density of states? Do you remember? So let me just
Maybe integrate over an x and y and z.
not integrating
Derivative.
the derivative. We just calculated all everything inside here, and we just want the shell, right? The energy shell. Okay, so first of all we can, but we actually don't need that because we know the formula of the volume of the sphere and we know the radius, right? This is the radius. So the volume would be 4 right? And then we only need the just the shell of the sphere. It would be the surface, that it would be the density of states. You can, of course, you can compute this, right? That the density of states is just the derivative of the numbers of states. This. Okay, but we can actually do this. This is very easy. So it would be 4 pi. But this is the, you didn't stop me. This is the radius square, right?
Mm-hmm.
So the density of states is 4 pi. This is d of a. This would be the, well, it's the volume and this is the total number of states. So if we take the derivative, this is, and the only thing that depends on the on energy here is this on this epsilon is this part. All of this is constant. And this would be the density of states. Okay, so the message here is that in this case, in the case of the particle of a box, the good quantum number is just, well, it's k, right? So everything that we computed, it was by means of this relation, right?
Why is the volume is n bigger?
It's the same case of here, right? We associated the volume of the sphere with the possible, with all the possible quantum states.
All the possible states.
Yeah, it's everything that it's inside. But actually, in the quantum case,
Okay, I got it.
I would put instead of plugging this diagram, I would plug something like this, right? It's NA, NZ, and X, and NY. And these would do spheres, right? Like, you will see in the next exercise exactly how it is, but these are spheres. And the spheres are these are energies that depend on NX, NY, and NZ, right?
Mm-hmm.
And in the so in this case we didn't have to take the continuous limit because, well, we actually kind of did. But if you take the n to be very big, you can take some sort of a continuous sphere, and then the derivative of the sphere is just the last shell. That is the density of states. So actually what you're asking is, if I give you a number of energy, a fixed number of energy, how many possible ways the system can be in, given that the system has to respect that energy. Okay?
Okay.
Was it clear?
Why is that the 4 pi r square? Why is it true? Because it's not like just the shell. It's some like delta like כאילו למה זה נכון? כאילו למה זה 4 פאי r בריבוע?
אוקיי.
כאילו אני מבינה את הרעיון, אבל זה לא באמת שזה הגודל של ה...
כאילו, את אומרת כי זה קוונטי, או כי זה סטטיסטי, או כי, כאילו...
כי כאילו אתה צריך לעשות נגזרת לנפח. זה לא שאתה פשוט יכול לקחת את ההיקף.
זה מה שעושה?
כן.
זה מה שעושה.
נכון? כאילו, זאת אומרת, כזה.
אבל יש לך נגזרת פנימית כאילו של ה-R.
כן, אוקיי. כאילו, מה שעשיתי פה...
DR, זה הכוונה שלי.
כן, מה שעשיתי פה זה שעשיתי משהו כזה, כאילו D... אוקיי, אני צריך לעשות את זה. Sorry. I need to do this, okay?
Yes, this I understand.
Okay?
But I didn't understand.
So I can do this, right? This is the same, doing D, R, and D, E, D and DR. So I just put this here, right? And then I got the 4 pi, but I need to multiply by the derivative of the radius with respect to it.
Yes.
Great? So
Okay,
that's how I
so-
got it.
אבל כאילו 4 פאי, פשוט להגיד שזה שווה 4 פאי r ריבוע זה לא בדיוק מדויק, לא? כאילו... לא משנה, בסדר.
את אומרת כאילו...
אחד למעלה.
את זה?
כן. כאילו אתה לא מכניס פה את הנגזרת הפנימית.
למה לא? אוקיי.
לא משנה, בסדר.
אוקיי.
הבנתי את ה...
Okay. Sorry, maybe. Okay. Okay, so this is very interesting because we can plug the different dimensions here. For example, if it would be the case, I did it for 3 dimensions, but if you repeat the same thing for 1, 2, and 3 dimensions, then you would see that the density of states in 1 dimension goes like 1 over epsilon. Okay. In 2 dimensions, it would be constant. And can you guess what would be the in 3 dimensions?
In 1 dimension, it goes like 1 over square root of epsilon.
Yes.
Why?
It's not, like you can do the result, and this is why one-dimensional systems are not stable in general.
Okay, I get it. You derive it like once.
And in 3 dimensions, it would be something like going to like epsilon. So let me just put this would be the so this would be the relation. So you can see that if you want to put a lot of energy on a 1D system, the system itself wouldn't support receiving more energy. And the systems in 1 dimension are usually not stable. That's why we don't have 1-dimensional crystals and things like that. And the relation that in 2D is constant, it's something good in like it's a good reminder for the exam. Like if you're in 2 dimensions and it's not constant, it can happen that it's not constant, but usually for exam it won't. So if you receive something constant, you should think, okay, so it's reasonable. Or in 1 dimension, in 3 dimensions, if you receive something of the square root of epsilon, you should think, okay, this makes sense. If you would receive something different, then you should think why. Okay, it's a good trick. Let's go. Okay, so there's something else that it's very, very important. Here I told you that it's a particle in a box, right? But I didn't specify which type of particle. But for example, if I have fermions, then I can put only 2 particles in the same state, right? So I should do. Okay, so each level of energy should can't take. If I have a system of many electrons, I should do something with the density of states. Does that make sense? What should I do? So let's think that I have
for a boson, right?
This is for a boson.
Maybe.
If a particle, this is in general. Has spin s, then you should multiply the number of degrees of freedom by 2s plus 1. Okay? So for example, if I have an electron, then and that would give it 1/2, right? Electrons have. Oh,
yeah,
so the total.
2.
Great. So I can put 2 electrons on each energy, on each state, right? So it's nice, okay? So it works. And in the case that the energy depends on a like radially, the density of states depend radially on the energy. Like here, like you can see that the density of states is this thing, and the energy is the radius, basically. Then you would have this form. This is the volume, okay? Let me write this and then I explain. Okay, so this is the first remark. The first thing, here we saw in a specific case, and this is more general. Okay, this is the first one, and this is the second one. So we did it in 3 dimensions. If we would want to do it in d dimensions, as I show you, the derivative of the volume, it will give you a surface, an area, on d minus 1 dimensions, right?
Mm-hmm.
This is always true. And then you take the surface of the ball. And did you know that there's a function, that there's a way to calculate the volume of a sphere with the gamma function in any dimensions? Mm-hmm. Okay, so if you can do that, then you can just put the derivative and get this formula for the area. Okay, so let's go for another example, very fast. Okay, just click here. Okay, let's think about a photon. Do you know what is the energy of a photon?
Yeah.
H bar.
H bar.
H bar omega times.
What you mean in with a certain?
With a number. Okay, so it would be something like this, right? In 3 dimensions.
Okay.
Right? There's a plus one. There's a plus one here.
This is for specific energy potential. Potential energy.
In general, I'm thinking in a box. Not in a box. In general, the photons have this energy. The particles of a photon has this energy because we are not talking of electrons on a certain potential. Okay, we're talking about photons. From here, you can see that the relation and the relation with the quantum numbers and the frequency, it would be somewhat easy. So okay, this is online. Okay, I just put, and so this is the total number of states, right? This is all the states that I'm allowed to have before the energy of the system. What geometric figure does this make? Remember that the ends must be bigger, so they are integer numbers bigger than 0.
Why is it bigger?
Because we are trying to compute the total number of states.
But why not smaller than epsilon? Like the epsilon is like the max, right?
Good catch. Okay. So if I would write the number of states here, what figure should I do to represent this geometry?
משולש.
Well, in 3 dimensions pyramid. So you can see here it's very nice because the vertices of the triangle of the pyramid are the when, for example, nx is this is this point, right? So it's bounded here by x, and you can have any combination on this inside this pyramid, right? And then what you do is that you only care about when this is equal, so on the surface of the pyramid. This is the density of states. Okay. So, do you know the formula for the volume of a pyramid? It is the base times the height divided by 3. Okay? Okay. So what's the base here?
nx and y addition.
Never. And you can see that these are the values, right? This is the length, and you have the same here. So instead of, it's not nx, it's this is epsilon over h by omega, right? And the height is the same. So this is 1/6. Epsilon q. And this is the density of states. Oh, the density of, this is the total number of states. And what would be the density of states?
epsilon בריבוע חלקי 2 h בריבוע בריבוע.
Okay. Cool. Great. Okay. Let's do a final, an exercise. These were 2 examples. Then let's do an exercise. Okay. So we are on a metal. And the average number of electrons for some energy you saw this formula already or not yet?
Yeah.
זה...
No, like
Yeah, exactly.
like Boltzmann.
It's not Boltzmann, it's Fermi-Dirac.
Fermi-Dirac, yes.
Right? The lowest energy is at minus V naught. Okay. Below the chemical potential. Okay. The question is how many electrons in the metal impact just write the picture and okay, so we have electrons that have this distribution of the energy. The lowest electrons are sitting here, okay, which is below this potential, and we want to know what's the probability of the electrons hitting these walls to go away from the material, okay? Makes sense? It's like the tunneling. So, do you remember the formula by any chance of the current density? The charge current density from electricity and magnetism?
Sigma.
That's the conductance. Here is the. Okay, so it's the electrons.
N.
Right? The density. Okay, so I will not write that. So it's the charge, right?
Times N.
Instead of N, I will put rho. Okay, which is density. And let's assume that the only velocity that counts is it's on the c direction. Okay, so the electrons are only moving on the c direction. So times the velocity, right? Okay, but we know how do we relate in quantum the velocity with the k vector? So up to a factor, we can write B set as HYK. Okay. So if we are asked how many electrons per unit area, so they are asking us to get the density, right? Because we know this, and we can plug the velocity. Okay. So these are the three quantum numbers, right? Dm. This is okay. So you can think of this as a box, right? As a potential box. So the idea is that we are going, like the steps that we are going to go is that we are going to go from the quantum numbers of a box to the momentum space that we know how to relate, of how we did it in the first exercise. So we can do, this is just volume over 3 pi cube. Okay. Which type of particle are electrons?
Fermions.
Right. So, as we know, like the factor that we need to multiply is 2, right? The 2s plus 1 is just 2. So the density of electrons is just given by the density function of electrons. So this is, you can think of this as how many electrons are in some energy. So this is energy density. Okay. This is how many electrons are in each number of energy. Okay, it's the occupancy number. So we can think like if we have the energy, then we have the density times 2. Right? So this would be the density. Okay? And then we can just plug the integral for to get the current density here. This is what we want. So we have rho Now, we just have to do the integral for k, right? There's something small that we are allowing that some electrons can return. Okay, so they hit here, they come free, and then they come back. Okay. So the charge density is given by 1. Okay, this is just schematic. This is the formula that we are going to use. Let me explain. This is all the electrons that come by. So these are all the electrons that can jump. And we're putting this on R factor that it just tell you how many of them return. So that's why we are subtracting that from the usual number. It's not something that we are given, just it's something that we are taking into account. Okay? So we can just plug in this formula that we have for the volume, for the infinitesimal volume. Exact. Then J just would be 1 minus R integral. So I just plug the formulas that we have for density and for the velocity in the c direction, because only the particles, we are assuming that we only care about the particles that are moving on the c axis. Okay. And so we actually are only integrating under k. This would be the density. Here I missed the mass of the electron somewhere. So if the momentum is k, h bar k. And just 1 minute. So the velocity, it would be h bar k over m, right? So this would be the momentum. And this comes from the beta here. this would be the charge density for the material, for the metal in this case.
כן, בוא נשאר להיכנס. לא. זה שום נחמדות.
היה פה פעם.
היי אלי.
צהריים טובים.
אתה לא שלחת לי את הלינק.
לא, אני אשלח, אין לי את המספר שלך שאני אשלח לך.
לא, שלחתי לי.
סליחה שלא הספקנו. האמת שהוא תמיד שואל משהו כזה באבחן, לא ברור.
פשוט אפליקציה שמשאיר לך את ההתקנה אוטומטית.
אוקיי, תודה.
רשמתי לך.
רגע, מה המייל שלו?
אלי,
אם אתם רוצים לראות פשוט נשמח.
כן.
210.
לא ג'ימל, BIU.
אני אשמח.
ואז למה זה לא עשה לי שום דבר? אני
תודה רבה.
מפגרת שאני שכחתי את זה, אני צריכה להכניס את הקובץ שקוראים לו משהו
אין שם איזה אתר שאני יכול להוריד על זה משם? או אם אני אחפש פשוט בגוגל את השם של זה?
זה או להוריד את זה דרך פייתון כספרייה,
יכול היה לי
שזה
שנייה
קצת התעסקות,
בעצמי.
או להוריד את זה דרך אפליקציה שעושה את הבאקים של הפייתון. אני מעדיף דרך האפליקציה כי זה מסדר לי את
כן.
הבאקים.
אוקיי, טוב, תודה רבה.
תודה.
אני לא יכולה לפתוח את הקודים
נתקדם ברוסית. נתן לעצמי גר ללמוד רוסית כי אני יכול לדבר עם עוד אנשים.
למה אתה רוצה ללמוד רוסית?
כי אז אני יכול לתקשר עם אנשים ולגרום להם להרגיש בנוח.
שלב הבא זה ללמוד מה שכן כל פעם
וגם קרסיב אני מסתדר יחסית עם זה, כי זה דומה לאנגלית ואני יודע קרסיב באנגלית.
עכשיו שנייה אני שואלת ג'ימי
אפשר לדבר
הרוב להיות הם אותו דבר.
אבל כשהוא בדק את הקומפלט שלי אז הוא שם לי ברייק פוינט.
אז כל עוד אתה מבין להמיר באותיות,
כאילו מה קורה
אז זה לא כזה מסובך. אלא זה בגלל שאני יודע לגרום למי שאני מולם להרגיש בנוח, זה יותר פרודקטיבי.
למה לא ערבית?
אני פחות עובד עם הערבים. אם הייתי מכיר את הערבים הרוסים הייתי עובד ערבית.
אני כאילו לקרוא או לפתוח?
השפה הראשונה שלמדתי היה יידיש בגלל החרדים.
אולי בתגבור זה קורה, אבל איך מלמדים אותנו לדבר?
מה עם ערבית?
ערבית זה שאני...
למה?
ערבית, אני לא מכיר ערבית.
לא.
אני יכולה להכיר לך כמה...
ערבית זה לא שפה שנכחדה כבר.
עדיין מדברים בה, יש מעגלים שעדיין מדברים בה.
אני צריכה לשנות הפריוריטי ולראות שזה בכלל לא רץ לי.
לא, גם הגמרא.
יכול להיות שזה שטויות.
כן. לא עושים מתמטיקה ופיזיקה הרבה פעמים. חרדים עושים, ואז כאילו אפשר לדבר איתה ביידיש.
טוב, אני אבין מה הסדר העדיפויות שלי ומסדר עליו. כי מחר בסדר, זה די
קודם כל זמן אבל
נכון, את נשארת פה?
תודה. אולי נסיים את זה. אני הבאתי משהו.
אם אתה רוצה להתחיל ספרדית,
שעושים עליה אנשים ככה דקת מזמן. זה כשאנחנו עושות שתינו, זה נראה לי...